Hello everybody, welcome again. Today in this lecture we're going to talk about intrinsic semiconductors. Actually the unit is named as semiconductor materials and diodes. Actually the part that we're going to talk about intrinsic semiconductors is only going to last about 5 minutes, but before that actually we have a huge introduction to make unless you have enrolled the semiconductors course before. And the reason for that is simple. Let me get into it. Most electronic devices are fabricated by using semiconductors along with some, of course, conductors and insulators, and that's the reason actually we're going to take a look at why semiconductors take a huge place in our discussion of electronic devices. And to understand the behavior of electronic devices or elements such as transistors, diodes, we need to know a few characteristics of semiconductors. That's why we are here. So let me get into it right this way. Silicon is by far the most common element that is used for semiconductor materials and fabrication of them. So Silicon Valley now makes sense, doesn't it? That's the reason. But of course, actually, we also have other semiconductors, and here actually I have a table for that. As you can see, we have elemental semiconductors and also compound semiconductors, and silicon is the most important semiconductor that we are using. And let me tell you this, the silicon is the most general form of semiconductor. What is that supposed to mean? Other semiconductors are generally used for specific applications, specific areas. For instance, in the compound semiconductors, here we have gallium arsenide, which is actually used for high-speed and optical devices, a specific purpose. However, silicon is a more general application semiconductor. Now, let's get into the main subject today, intrinsic materials. Actually, we're going to talk about intrinsic semiconductors, but that actually applies to intrinsic materials too. First of all, let me ask you a simple question. Actually, we have nothing to do with this periodic table right now, but how do you represent an atom? So let me actually take my pen and show you. If we have an atom, that atom actually consists of protons, that's for sure. And then actually we also have neutrons, right? Am I pronouncing that right? Then we also have electrons. 3 different groups. So the thing is, actually, we got to represent them. And protons and neutrons are found in the nucleus. However, electrons are found in the shells we have. And basically, these shells are encapsulating the nucleus we have. So basically, the best way to represent an atom is this. I'm going to draw a circle. This is the nucleus, right? And then I'm going to have a shell. This is a shell and another shell. Let's say this particular one has 2 shells. And here we have some atoms like this. These are actually, by the way, electrons. Sorry, not atoms. Oh, misconception. I hate it. So here's the thing. One of the main things in the representation of an atom is this. Here we have actually a distance between the nucleus and also the shells. And if that distance increases, the energy of the electron increases too. So the electrons in the outermost shell is called valence electrons. That's important. And notice that this is the outermost shell and this one is the innermost shell. So this information is quite enough for now. What you got to know is that the electrons that are found in the outermost shell are called valence electrons. And valence electrons are really important since they determine the chemical activity of an element. What is that supposed to mean? If you have 2 valence electrons and 3 valence electrons, those are 2 different things. I mean, it affects the chemical activity of the element. And that's the reason in periodic table, actually, the elements are ordered according to their valence electrons. And on the left, actually, you can see a portion of the periodic table. I mean, we don't need the whole periodic table, but this portion is actually showing us where you can find your semiconductors. And let me tell you something about this. A semiconductor is actually divided into 2 groups. You may have your semiconductor as an elemental one, or you may have it as a compound. And now, let's specifically take a look at silicon atom, which is really important, as I told you in the beginning of the lecture. And actually, the thing in here is that not all the elements, as you can see on the portion of the periodic table, is an elemental semiconductor. Some of them are actually not semiconductors directly, but they are compounds with some other elements may yield a semiconductor. Like what? Like gallium arsenide. say gallium arsenide in here. Gallium is not a semiconductor itself. Arsenide is not a semiconductor. Arsenic is not a semiconductor on its own, but their compound is a semiconductor that is used for high-speed and optical devices. So we're going to take a look at silicon atom. So what I know is silicon is actually have an atomic number of 14, right? So silicon 14. And do you know how to write the electron configuration for silicon? I actually do, but you don't have to. So 1s2, 2s2, 2p6, 3s2, and 3p2. And let's count 2, 4, 10, 12, and 14. Yes, that's correct. So this is actually the electron configuration of silicon. And notice that actually here we have the third shell, and in the third shell we have 4 electrons, meaning that actually our silicon is having 4 valence electrons. Let me draw a silicon in here. Let's say this is the nucleus. Then we have this first shell. In that shell we only have 2 electrons. Let me draw them. And then we have another shell in which actually this is the first shell. Then here we have the second shell in which actually we have 8 different electrons. 1, 2, 3, 4, 5, 6, 7, 8. Great. And we also have another shell which is the outermost shell, and in that one we actually have 4. 1, 2, 3, and 4. So basically this is how we represent silicon atom. So the thing that I need to get your attention is that what would happen if we interact 5 silicon atoms at the same time. What is that supposed to mean? Each will have 4 valence electrons. So let me draw one. Here we might have a silicon, and here we might have another one in here, another one in here, and another one in here. In total we have 5 silicons, and each of these silicons actually have 4 valence electrons. Now let me actually draw the figure representing the valence electrons of each silicon atom without interacting them. So here we have 4, another 4, another 4, but note that these silicon atoms are not interacting with each other at the moment. So this is what we're going to have. But my question for you is that for the interaction, there should occur a covalent band, right? They need to share their atoms in order to interact with each other. And in that case, our silicons will share their atoms, and this is going to be something like this. I'm going to delete these two. Since they're sharing their atoms, this is the band we have in there, and here we will also have it exactly the same thing, and also in here. So basically we're going to have these bands, and these are actually covalent bands. And now this is actually the crystal clear version of the interaction of silicon atoms with each other. And the thing in here is, in this figure, we see a 2-dimensional representation of the lattice that is formed by 5 silicon atoms. And actually, there is a configuration for that, where did I put it? Oh my god, it is right in here. I'm sorry, I misplaced it. So this is actually the configuration that is called tetrahedral configuration for this particular silicon interaction between 5 silicon atoms. So why does it matter? Here's the thing. In the figure right in here, we have a representation of a silicon single crystal. And at T is equal to 0 K, and K is Kelvin and T is temperature, by the way. Let me put it right in here. At T is equal to 0 Kelvin, each electron is now at lowest possible energy state. And even we apply a small electric field to this material, the electrons will not move because they have the lowest possible energy now. But or let me just put it this way. Therefore, at T is equal to 0 Kelvin, when temperature is 0 Kelvin, we could say that silicon is an insulator. And that's actually the best part of having a semiconductor. It may actually act like an insulator sometimes and also conductor sometimes according to your need. And that's the reason why we are using semiconductors. We have the flexibility. So what I'm going to say is right now is at T is equal to 0 Kelvin, silicon is an insulator. Oops. So what do we mean by saying silicon is an insulator? Basically, we are saying that no charge will flow through the silicon. No charge flow. But obviously the question comes in the way, but what happens if temperature increases? So let me scroll the page down a little. If temperature increases, the valence electrons may get or may gain thermal energy, and this energy may break the covalent band so that electron might move away from its original position, just like the figure that we have in here. Originally the electron was actually placed in here. Since actually it gains some thermal energy, it is able to break free the covalent band it has, and then actually it moves right in here somewhere random. It doesn't matter. And here comes a really important definition, which is that the minimum amount of energy required to break the bond is called band gap energy. This is pretty important. Band gap energy. I'm gonna put that definition right in here because you're gonna hear that a lot and we're gonna use it a lot. So band gap energy is basically the minimum energy required to break the bound. This is the definition of band gap energy, and one important thing is that band gap energy is measured in electron volts, and also it is denoted by Eg. These are important information. Now, the electrons that break the line, that break the bond, and also they are breaking free, move through the crystal, right, randomly, and actually this process generates current. As I told you in the beginning of the introduction lecture, then actually a charge. I gave you the definition of electronics, right? And in that we told you that the motion of charge in vacuum, gas, or semiconductors is the main subject, and this is actually why where we are ending up with. So that makes sense. So now we will make up a couple of observations by checking out the figure we have in here. So the thing is, by the way, this is an energy band diagram. This is really important. So let me put that in here. Energy band diagram. So basically in here, actually, we have some energy levels, as you can see, EC and EV. EC right in here is going to be the minimum energy of the conduction band. And EV is going to be the maximum energy of the valence band. And the difference between them, which is going to be Eg is equal to Ec minus Ev, is going to be our energy band gap. This is pretty important. Band gap energy. Another important notation in here is that, as you can see on the figure, but it is not that clear, this is actually the conduction band we have. And as you can understand from the name, it is conduction band. And in here we have the valence band. So basically the logic is simple. Whenever an electron moves from valence band to conduction band, by having enough band gap energy, we're actually going to have the conduction. And also notice that the area between two bands is called forbidding gap, and if an electron gains enough energy, it moves from valence band to the conduction band, which is called generation, which is basically the conduction of current, let's say for now. Since we have talked about energy gaps, the idea in here is that materials that have large energy gaps are called insulators. So actually this is worth taking a note in here. Let me put an asterisk. If energy gap is high, then the material is likely to be an insulator, because at room temperature, essentially no free electrons exist in the conduction band. That's the reason why it is an insulator. You gotta have some electrons in the conduction band in order to be a conductor. And in contrast, the materials that have more electrons in the conduction band at room temperature will be, as you know, are conductors. That's the logic we have. And semiconductors are actually between them. They have an energy gap around 1 electron volts. That's also important. Let me put that in here. Energy band gap of a semiconductor of a SC, you can understand, is around 1 electron volts. For instance, silicon has a band gap energy around 1.1 electron volts, and for gallium arsenide this value is around 1.4, I guess, as far as I can remember, but you don't have to remember it unless you have a math professor. So now with this information we are going to move forward with the concepts of holes, and which is really important. So the net charge in a semiconductor is 0. That means our semiconductor is neutral. If an electron breaks free, it leaves its original position and leaves an empty space. That makes sense, right? Because imagine, actually, this representation is not a good one, but this is a modeling, so I can do that. Fuck it. So let's say actually we have these 3 spaces, and each of them we have electrons, all right? And if one of the electrons gain enough energy and breaks free this bond, there will be an empty space right in here, all right? So as our temperature increases, more electrons will break free and more empty states are created in that sense. And the neighbor electron of the empty space, for instance, if this one actually gains enough energy and leaves, then we will have an empty space in here, and the neighbor in here might actually move into empty space. And it seems like a positive charge moving into empty space. So that positive charge is called a hole. So I know this is a little bit weird idea, but it is actually a great one. And also note that this explanation is oversimplified since you have to gain the prior knowledge. If you want to find out more about holes and electrons, we also have a Fundamentals of Semiconductors course, which I really recommend you to go and check out. If you are looking for a discount, please message me. I will give you the discount as since you're our student. Since you're our student right now, we're of course going to give you the discount. So let's move on. So now we will have a really important note in here. 2 types of charged particle contribute to the current in a semiconductor, and I'm actually going to put that in here, and I want you to take notes. The first one is obviously electrons, which are negatively charged, and the second one is holes, and they are positively charged. So these are really important notations. You should really take a note. So of course, since we have electrons and holes as our charged particles that contribute to our current in a semiconductor, the concentration of electrons and holes are really important, and that's why they take a huge place in our study. And that's the reason why actually we're going to take a look at some materials, and in those materials actually we are going to make some comparisons between the concentration of electron and holes. For instance, now we are going to talk about intrinsic semiconductors. In an intrinsic semiconductor, N0 is going to be equal to P0. And right in here, N0 is standing for electron concentration, whereas P0 is standing for hole concentration. So basically, in an intrinsic semiconductor, you have exactly the same concentration for electrons and holes. And also intrinsic carrier concentration, actually, which is going to be exactly the same with these values, since they're equal to each other. We put a common name. Instead of saying electron concentration in an intrinsic material, we say intrinsic concentration. In that sense, you can easily understand that we are talking about an intrinsic material or a semiconductor. So N0 is equal to P0. They are equal to Ni, and this one is called intrinsic concentration. And we have a formula for that, and that's actually the whole idea behind this lecture. So Ni is going to be equal to B times temperature, and this B is, by the way, a coefficient, which I will give you the details later. This T is temperature, but that's not only T, but we're going to actually have 3 over 2 power of the T times E2, and here we are going to have a parenthesis minus Eg, which is going to be the band gap energy over 2kT. This K in here is Boltzmann's constant, however you pronounce it. This is just a constant, and T is again the temperature, and this is the band gap energy we have. So this is actually pretty easy formula, and actually we are going to evaluate this formula and check out if it holds. Yeah, it holds, but we are going to actually solve a couple of examples in the next lecture. And by the way, when you are solving questions B and G, and when I say G, I'm talking about the band gap energy, they are given. unless you're expected to know, unless you have a mad professor. Because first of all, the band gap energy and also B values, B is a coefficient, they depend on the type of semiconductor you have. So it is really hard to memorize all the values for each semiconductor, and also it doesn't make any sense, right? Why would I memorize it if we already have the tables? So in the next lecture, we're going to solve two examples about intrinsic semiconductors. I hope you will be there. I will be there. And by the way, if you have any questions, please do not hesitate to ask. I'm always here to help you out. So thank you for watching.
Hello,
and see
everybody.
you in this video. We are going to solve an example about intrinsic concentration, which is basically the concentration of electrons and holes, which are exactly the same, by the way, since we're talking about an intrinsic material. We are asked to calculate the intrinsic carrier concentration in silicon at T is equal to 300K. So as I said in the previous lecture, you are generally given the values of B and also the band gap energy. And let me, by the way, put the formula so that you can understand better what I'm saying. So the intrinsic carrier concentration, which is denoted by Ni, is going to be equal to B times T2 3/2 times E2 minus Eg, and this is band gap energy, over 2kT. So basically, you will be given the values for B and also band gap energy, because those are special to semiconductors. I mean, each semiconductor has its own value, and I'm going to give you those values. B for a silicon is going to be something about, let me check from my paper, 5.23 times 10 to 15. And also band gap energy, as far as I know, is about 1.1 electron volts. And also here we have K, which is Boltzmann's constant, and it is about 86 times 10 to minus 6. So now we can easily solve the question. First of all, Ni is going to be equal to, let me put the B value, 5.23 times 10 to 15. And then actually we're going to have temperature to, oops, instead of putting temperature, just let me put the value, which is 300K with the power of 3/2 times E2 minus Eg, which is minus 1.1 over 2 times 86 times 10 to minus 6 times the T value 300. This is the equation we have, and in the end you're going to end up with the answer of 1.5 times 10 to 10 1/centimeter cube, and this is the answer. And by the way, let me tell you something. I have encountered a lot of students having problems with calculating this part, which is actually a little bit of a shame. So let me tell you the best way possible to do this. So basically, whenever you have 3 to the power of 3/2, that basically means that you're actually taking the cube of t, then actually you're taking the square root. That's the logic. So in your calculator, you can use this trick too. Now I'm going to move on with the other question I have, which says calculate the intrinsic carrier concentration in gallium arsenide and also germanium at T is equal to 300K. So first of all, again, let me put the formula. Ni is going to be equal to B times T2 3/2 times E2. Here we are going to have minus Eg over 2kT. This is the formula we are going to use. And B constant values for, first, let me put that for gallium arsenide. It is about, let me check my notes, 2.10 times 10 to 14. And for germanium, germanium, that value is going to be about 1.66 times 10 to 15. And what about energy band gaps of these two semiconductors? E.g. gallium arsenide is going to be something about 1.4 electron volts, and E.g. germanium is going to be about 0.66, as far as I can remember, 66 electron volts. Now, with the information we have, we can easily solve the question. First, I'm going to say intrinsic concentration for gallium arsenide is going to be equal to 2.10 times 10 to 14 times 300 to 3/2 times E2 minus Eg, which is minus 1.4, over 2 times 86 times 10 to minus 6 times 300. And in the end, that is going to be equal to, let me check, 1.79 times 10 to 16. That's the answer for gallium arsenide. And what about germanium? For that, we are going to have in here 1.66 times 10 to 15. and then we're going to have exactly the same temperature value, and then we're going to have E2, but this time we have a different band gap energy, which is 0.66 over 2 times 86 times 10 to 6 times 300, and in the end the answer is going to be 2.4 times 10 to 13. And of course units are important. Here we're going to have as you know, centimeter, 1 over centimeter cube, and here we are also going to have 1 over centimeter cube. And this is the answer. And this is, by the way, the end of the video. If you have any questions, you can always ask your questions by using Udemy's message box or our mail address or our WhatsApp question line. It doesn't matter. All we want is for you to be able to ask your questions at the right time. So thank you for watching, and see you in the next one. Hello everybody, in this video we are going to talk about extrinsic semiconductors. In the previous lecture we talked about intrinsic semiconductors, in which actually we have learned that N0 is equal to P0. So let me put that equation in here. In an intrinsic semiconductor, N0 value is equal to P0 value, where this N0 is actually the electron concentration and this P0 is the hole concentration. And we also know that these values are equal to Ni, which is the intrinsic carrier concentration. This is what we have learned. And since this is the case, in an intrinsic semiconductor, very, very small currents are possible. However, of course, you can change these concentrations. You can manipulate these concentrations by adding some impurities. And that's actually the logic we have in here. For instance, let's say we have an intrinsic semiconductor. In that case, whenever we add an impurity, we are able to get an extrinsic semiconductor. And that's actually going to be more useful in a sense that we need a current flow through the semiconductor we have. So, for silicon, I mean, since we started our debate or discussion from silicon element as a semiconductor, let's move on with silicon. For silicon, we add these impurities and we generally take these desirable impurities from group 3 and group 5 elements. So let's see what happens if we choose the impurity atom from group 5. Let's choose phosphorus, and as you can see on the figure right in here, we replace a silicon atom with a phosphorus atom. So what happens in this case? Before actually getting into anything, let's analyze the phosphorus atom just a little bit. So generally phosphorus atom is denoted by a capital P and it has an atomic number of 15. So we can put the electron configuration in a simple way as 2, 8, and 5, meaning that our phosphorus atom has 5 valence electrons. So this actually may cause a little bit of a problem. You know why? Because since we are replacing our phosphorus atom, silicon atom with phosphorus atom, the typical silicon atom had 4 valence electrons, which was actually sufficient enough to satisfy the covalent bond we have over there. But this time we have 5 valence electrons. Yes, 4 of them are actually going to satisfy the covalent band again, but the problem is there will be 1 electron free. And actually that's the whole point, so you got the idea. So again, let me repeat here. Phosphorus atom has 5 valence electrons. So 4 of them will actually goes into covalent band, and 1 of them is actually loosely bound to the phosphorus atom, meaning that the bond is not tight. At room temperature, this 5th electron can easily break free, and this is the whole idea behind this extrinsic semiconductors. Thus, that electron can move through the crystal with ease and therefore creating current. That's the logic. And also, let's have a look at this figure right in here. In here, the 5th phosphorus atom goes into conduction band. As you can see, it leaves the area and goes into the conduction band, and a positively charged ion is created. This is also pretty important. So far, the story has been great, but let's look for the terminology. So the phosphorus atom in this story is called a donor impurity. So let me put that in here. The phosphorus in this story is called a donor impurity, and you can easily guess the idea behind donor impurity since it is donor, right? Because it donates an electron that is free to move through the crystal. And the thing in here is that as a result, when a donor impurity is added to the semiconductor, free moving electrons are generated, because logically we actually have an electron from group 4, which is silicon, which has a valence electron in an amount of 4. But this time actually we are bringing another atom having 5 electrons in the valence shell. Therefore, actually, this causes one electron to be free and moving in the crystal. That's the logic we have. But the most important operation in here, we are creating moving electrons, but without generating holes. We don't have any holes at all. And this process, by the way, is called doping. Have you ever heard this before? Doping. It is actually called doping because now we are able to control the concentration of free moving electrons by adding impurities. That's the logic we have. So this is actually the donor case, meaning that we have chosen our impurity from group 5 element. But now let's see what happens if we actually take a look at an impurity that is chosen from group 3. But before that, actually, let me tell you the most important thing about this type of impurity. If a semiconductor contains donor impurities, it is called an N-type semiconductor. This is the most important point of this lecture, N-type semiconductor. And the logic behind this naming is pretty simple. Remember the time that I told you in an intrinsic semiconductor N0 is equal to P0, then I told you that N0 is standing for electron and P0 is standing for hole. And since actually when we have a donor basically donating a free moving electron, so basically it is giving the electron. So in that sense, actually we are having more electrons than holes. So that's the reason why we call this type of doping as N-type semiconductor, because now we have more electrons than holes, and holes are, by the way, represented as a P. So keep that in mind. Now we are going to take an impurity from group 3. And the most common one is boron atom, which is denoted by B and has an atomic number of 5. So the basic electron configuration is 2 and 3. In that sense, this time we have a valence electron in an amount of 3. So that's problematic. You know why? Because we know that our silicon has 4 valence electrons to, satisfy the covalent band. But this time we have 3. So how are we going to satisfy the covalent band at all? So check the figure in here. As you can see, this time we are replacing our silicon atom with a boron atom. 3 valence electrons of boron will satisfy 3 of the 4 neighboring silicons. That's fine. And that actually leaves us a 1 empty space, an empty state, whatever you prefer to call. And this is the important point, by the way, because logically think this through. In an N-type semiconductor, we had more electrons than holes, and this time we are supposed to have more holes than electrons. So since we are actually working with an atom that actually has less valence electron than the silicon, it is of course going to leave a space empty. That's the logic we have. And at room temperature, neighboring silicon valence electrons will have sufficient thermal energy to move into this empty position. So a hole is going to be created. That's the logic we have. And since in this story, a boron atom has accepted a valence electron, because the basic logic is this, our boron is actually getting an electron in order to satisfy the covalent band. But that is actually causing our silicon atom to lose 1 electron, meaning that gain a hole. That's the logic we have. It is amazing. Now, since again boron atom is accepting a valence electron, it is called an acceptor impurity. Let me put that in here, acceptor impurity. And acceptor atoms lead to the creation of holes without actually generating electrons. This is the important point, because donor impurities are actually creating electrons without generating holes, and acceptor impurities are creating holes without generating electrons. This is the importance of this whole thing, because generally an electron and a hole comes within together. They're like a package together. But the thing is, in order to break the equality you have in an intrinsic material, what you got to do is you got to change the acceptor impurity, or I mean, you're going to just, add an impurity, which is either acceptor or donor. And by the way, I have just noticed something. In the titling of this PDF file, there has been a mistake. Actually, the first one is right, but the second one is not correct. This was supposed to be extrinsic semiconductor. I'm so sorry for that. Now, let's move on. And let me also tell you, this process is called doping again. This is also doping because this time you're controlling the concentration of holes. So basically, doping, as you can understand from the name, it is either controlling the amount of concentration you have on the electron or the holes. So this one is also called doping. Let me put that in here. Maybe you want to see that while you're taking notes. Doping. And right at this point, story time ends and we get into equations which are really important. So the relationship between electron and hole concentration in a material, in a semiconductor, is determined by an equation involving our intrinsic carrier concentration, and which is, by the way, really easy. And by the way, I forgot to show you the figure we have in here, but it is not that important. I mean, it is just a figure, but basically the idea is this. Here we have a boron atom, right? And it actually misses one covalent bond in here. So basically, actually, we're getting that electron from another silicon and creating a positive charge over there, meaning that we're creating a hole in silicon atom. I already told you that. Now, let me actually show you the relationship between electron and hole concentration in a semiconductor. Basically, we have N0, which is, by the way, going to be the electron concentration. Let me put that in here because these definitions are really important. Electron concentration. Then we also have P0, and that is actually standing for hole concentration. We also know that. So we are actually basically going to be talking about these two, and we are going to define a relationship between them. And that relationship will also include intrinsic carrier concentration. When we multiply these two quantities, they will be equal to the square of intrinsic carrier concentration. So this equation is pretty important because generally we already have the intrinsic concentration, intrinsic carrier concentration for semiconductors. For instance, for silicon, we have an intrinsic carrier concentration about 1.5 times 10 to 10. So in a way, if we just add an impurity, we can easily calculate the electron and hole concentration. That's the logic we have. And furthermore, actually, we can rearrange the terms a little bit. Actually, we're going to manipulate this equation. How so? So first of all, let me tell you this. At room temperature, and we are generally talking about room temperature, which is 300 Kelvin, each donor atom donates a free electron to the semiconductor, right? So that's logical. We already talked about this. We already went through this. So let's say we have ND, which is the donor concentration, a capital N and D, which is the donor concentration. And by the way, I don't want you to misunderstand the concepts. So actually, I will clarify everything. Let's say this is donor concentration, but this is actually the worst handwriting ever, concentration. The thing in here is that this N0 is electron concentration, but this ND is donor concentration. Since actually you may assign, or you may think in your head, I mean, you may make a little bit of mapping, electron means donor, but it is not the way it is. Actually, electron concentration in the material is something different, and the donor concentration you have is something different. So if you have a donor concentration ND, which is a lot greater than the intrinsic carrier concentration you have. So basically, if ND is a lot greater than Ni, basically you can see that the donor concentration is approximately equal to the electron concentration you have. So what is that supposed to mean? Basically, when you think about it, in an intrinsic material, and by the way, in an intrinsic material, the intrinsic carrier concentration is nearly equal to the electron concentration. So what I'm saying is, if you have too many donor concentration on your hand, and when you add that impurity to your material, it is going to end up with actually having all the electron concentration could be defined as the donor concentration. It could be a better definition when you think about it. I mean, you have a less amount of electron concentration that could easily be ignored. And you want to know the reason. Since the donor concentration is too much, since it is too big, you can simply ignore the electron concentration. That's the simple logic we have. And when we do that, actually, our equation can easily be manipulated. And the reason for that is, let me put the equation in here. N0 times P0 is going to be Ni squared. So when Nd is a lot greater than Ni, we can say that the donor concentration is going to be equal to the electron concentration. So in a sense, instead of this N0, we are going to have Nd times P0, that is equal to Ni squared. And right at this point is really important because you are adding the donor concentration. So you know the amount of concentration you have in your hand, but you don't know the whole concentration in the material. And you already have the intrinsic carrier concentration. So if you want to find out the whole concentration in the material, you can simply use this formula. So that's the logic we have, and it is actually going to be a really useful one later. And similarly, actually, at room temperature, we have a similar formula for Hall concentration too. At room temperature, each acceptor accepts a valence electron in a semiconductor. We already have that logic. And let's say this time, actually, we are having an acceptor. This is going to be a subscript. Let's say this time we are actually having an acceptor concentration, which is Na. And let's say that concentration is a lot greater than the intrinsic carrier concentration. Is that right? Yes. And let's say this time you have an acceptor concentration that is a lot greater than the intrinsic concentration. In that sense, actually, what we're going to assume is the whole concentration is going to be equal to approximately is going to be equal to acceptor concentration. And in that sense, again, we can manipulate the equation we have. N0 times P0 is going to be equal to Ni squared. And we can simply say that this P0 is going to be substituted by Na. And 0 times Na is equal to Ni squared. So basically the logic is the same. Since you are adding the impurity, you know the acceptor concentration, but you really want to know the electron concentration in the material. So what you're going to do is leave electron concentration alone, and then say Ni squared over Na is going to be equal to the electron concentration I have. And this is going to be a really useful formula for later use. So this is actually pretty much everything about extrinsic semiconductors. In the next video, we're going to solve two examples about that. Not problems. They're going to be easy examples, and we're going to use these formulas we have found for electron and hole concentrations. As you can see, the topic is really easy. So thank you for watching. And by the way, if you have any questions in your mind, please be my guest and always ask your questions. Thank you for watching, and see you in the next one. In this video, we are going to solve two examples about extrinsic semiconductors. So the first one is calculate the thermal equilibrium electron and hole concentrations. That's actually a great question. So first one is option A, and it says consider silicon at T is equal to 300 K, which is basically the room temperature, doped with phosphorus at a concentration of Nd that is equal to 10 to 16, 1 over centimeter cube. Recall from example 1.1, which is actually the previous example that we have solved on intrinsic carrier concentration. We know for silicon Ni is equal to 1.5 times 10 to 10 1 over centimeter cube. So actually that's an excellent question. And in the previous lecture, let me go back to that PDF. I told you that we are going to use these electron and hole concentration equations. And I also told you that whenever actually you want to find out the whole concentration when you are adding an impurity that is donor concentration, I told you that you already know the donor concentration because you're adding the impurity. So in that case, you also know the intrinsic carrier concentration. So what you got to find out is going to be the whole concentration. And this is the example of it. So we know the donor concentration, which is 10 to 16. And we also know the intrinsic carrier concentration. So the only thing that is left is going to be the whole concentration. So how are we going to find it? So basically, in this particular example, the donor concentration, which is Nd, is a lot greater than our Ni value. And that's the reason, actually, we can think of this donor concentration as our electron concentration in the material, but this is just an approximation, so keep that in mind. We are not saying they're exactly equal to each other, but the logic is this. Let me give you numbers so that you can easily understand. So in an intrinsic semiconductor, let's say you have an I value, which is the intrinsic carrier concentration value, as 5,000. So that 5,000 is also exactly the 5,000 you have for electron and hole concentration. So let me say this is Ni, this is N0, and this is P0. So the logic in here is that later you decided to include an impurity with a donor concentration of, let's say, 100 million. How does that sound? So when you compare these two numbers, are actually this impurity is a lot greater than the intrinsic carrier concentration you have. So in the end, actually, what you're going to have is for N0 value, you're going to have 1 million plus 5,000. So what we are saying is that this 5,000 is actually can be ignored, and the reason for that is actually we're making an approximation. Since we have 100 million, I don't care about 5,000. So this is just an approximation, and this is the logic we have. So I'm going to delete this part because this has nothing to do with the question. Now I'm going to move on with the question. So we already have made our approximation, and then we're going to remember the formula we have. Normally N0 times P0 is going to be equal to Ni square. However, in this case, since actually Nd is a lot greater than Ni, we're going to make the approximation N0 is equal to Nd. So we're going to replace this one by Nd. So we will have P0 that's going to be equal to Ni square. And notice that actually we are interested in the whole concentration in here, which is P0. So P0 is going to be equal to Ni square over Nd. And that is going to be 1.5 times 10 to 10 square of that over Nd, which is 10 to 16. So in the end, the answer we are going to have is going to be 2.25 times 10 to 4. And of course, this is going to be in 1 over centimeter cube unit. So this is the answer for part A. Let's move on with part B, in which actually, again, we are going to have exactly the same silicon at exactly the same temperature. But this time, actually, we are having a boron. So that actually gives you the idea of what kind of concentration we're going to have. We're going to have acceptor concentration. This is a different type of doping. And this time, actually, the concentration for acceptor we have is 5 times 10 to 16. And again, let me remind you that Ni, which is the intrinsic carrier concentration for silicon, is about 1.5 times, oops, what kind of 1 is that? So let me delete that. 1.5 times 10 to 10. So the logic in here, again, exactly the same. Since Na is a lot greater than the Ni value we're going to have, so we can easily conclude that P0, which is the whole concentration, is approximately equal to Na. And that's why actually in the equation N0 times P0 is equal to Ni square, we're going to replace our P0 by Na. And then we're going to multiply it by N0. So that's going to be Ni square. Since we're looking for the value of electron concentration, we're going to leave that alone. So that's going to be equal to Ni square over Na. So in the end, since we know Ni is 1.5 times 10 to 10, we're going to put that, take the square of that over Na value 5 times 10 to 16. So in the end, when you do the proper calculations, what you're going to have is 0.45 times 10 to 4, 1 over centimeter cube. And this is the answer. And this is, by the way, end of the video. But before ending the video, I want to make an observation. As you can see, actually, the donor and also the acceptor concentrations are not that different. So the acceptor concentration is 5 times 10 to 16, and the donor concentration is 10 to 16, only just 5 times greater. So it is not a huge difference. Before ending this lecture, I want to actually make an observation. Notice that in here, we actually have a donor concentration in an amount of 10 to 16. And in here, we have an acceptor concentration, which is 5 times 10 to 16. So basically, according to that, here we are going to have a concentration of electron. And also here we are going to have a concentration of hole according to those values. So we have 5 times relationship between Nd and Na, acceptor concentration and donor concentration. But what happens if I just divide 2.25 by 5? Right? In that case, I would get 0.45. So as you can see, according to amount of impurity you give to the material, you get exactly the same reaction as the hole or electron concentration. So that's the logic we have in here. And Imagine a situation that we both actually gave acceptor and also donor impurities at the same time. So if that's the case, actually, finally, our material would be N-type or P-type. This is the question I have in my mind. So basically, we have calculated P0, which is 2.75 times 10 to 4, right? And also we have calculated N0, which is 0.45 times 10 to 4. So in that case, we would clearly have a P-type material since we are having more holes than electrons. So that's the logic we have. So this is the end of the video. If you have any more questions regarding the lecture, or it might be not about the lecture, it might relate to something else totally different, it doesn't matter, please ask your questions. We are always here for you. So thank you for watching and see you in the next one. Hello everybody, in this video we are going to talk about drift current density after explaining the creation of electrons and holes. If you remember, actually we talked about this for a while and we said that if you don't have electrons and holes, then you're not able to create current in a semiconductor. So basically the reason we have current through a semiconductor is that we have electrons and holes, and they're also moving through the material. So if these particles moving, then we have a current that is generated by these, and we refer these charged particles, by the way, as carriers. And this is an important notation, an important definition you will see often. So let me put that in here. We have electrons and holes, and they are called carriers. And another important notation in here is that if electrons and holes move, then we create or generate current. This is an important logic. And what we want to do right now is to dive into a little bit about this, movement of electrons and holes. How is that working actually? So there exist two basic properties, two things that make electrons and holes move in a semiconductor, because they're not moving randomly. Of course, there is a reason behind their movement, right? Imagine you have a car, right? I mean, if you don't apply a force, that particular car does not move. That's the logic we have. I mean, in order to make something move, you gotta apply a force, right? Or you gotta apply something. I mean, it's just not gonna, start moving without applying anything. So that's actually the reason we're gonna dive into more detail. So we have two concepts. The first one is drift, and the second one is diffusion. And when I say drift, I know most of you guys think about Need for Speed or something like that, the game. But drift in here is actually a little bit different. So these two concepts are pretty important, and we're going to check out them in this lecture and probably in the next lecture. So in this lecture, actually, we're going to talk about drift. So let me first put them. We have two things, drift and also diffusion. And these are actually making our electrons and holes move. So let me just say these are the reasons for electrons and holes move. And what is drift anyways? Drift is, by the way, the movement that is caused by electric field. So basically we have an electric field that actually is the reason for our electrons and holes to move. So let me just put that in here, movement by electric field. That definition would be sufficient enough. And what about diffusion? Diffusion is the flow that is caused by variations in the concentration. So what is that supposed to mean? Let me first put it right in here, variations in the concentration. So basically what we are trying to say is that we have a concentration of electron and hole, right? And in those concentrations, actually, we have some gradients. So what is that supposed to mean? Let's actually imagine an apple tree, all right? In an apple tree, you don't seem to find apples everywhere. I mean, in some areas, the apple is rare, right? And in some areas, you can so frequently find apples. Right? That's the logic we have, actually. That's what we mean by we are having a gradient in the concentration. That's the logic. And the reason for these gradients can be, non-homogeneous, homogeneous. And the reasons for these gradients could be non-homogeneous doping distribution. That's the one reason, or a few other things that we might talk about later. So it is not a topic that we need to discuss right now, but just know that there happens to be some gradients in the concentration. So in this lecture, we are going to talk about drift current density. So drift current density, to actually put it in a good way, an electric field is applied to semiconductor, right? So let me go down a little, let me draw a line. Here we have a semiconductor and we are applying an electric field to that particular semiconductor. So this electric field actually creates a force that acts on free electrons and holes. So basically, let me do a scheme like this. This electric field is creating a force. So let me just say creating a force, and that force actually acts upon our holes and electrons so that they move, holes and electrons. And that's actually the reason free electrons and holes experience a net drift. Now, we're going to consider an N-type semiconductor, and let me remind you that when I say N-type semiconductor, that means we're going to have more electron concentration than hole concentration. And actually, we have a figure for that. As you can see, now we have an applied electric field, right, which is in the direction from left to right. And notice that the drift velocity that our electron has is from right to left, which is in the opposite direction of electric field. And we also have Jn, which is, by the way, drift current density, which is in the exactly the same direction with electric field. So basically, electric field applied in one direction, it doesn't matter if it is from left to right, right to left, and that produces a force in the opposite direction. So the force is not shown in here, but according to this direction, the electric field is created from left to right, so the force is created from right to left. And the reason behind this is very, very simple. Electrons have negative charge. That's the reason why we have force in the opposite direction to electric field. And with that force, actually, electrons obtain a drift velocity, as you can imagine, because Newton's first law, which is F is equal to A times M. Force is equal to acceleration times mass. And of course, electrons might be a little bit about quantum physics, and actually we talked about this in semiconductor course. However, you may also have the idea of electrons as a particle. So in that matter, F is equal to AM. So if actually there is a force, then the electron is of course going to accelerate, and due to the acceleration, it is going to have some sort of speed. That's the logic we have. So that speed actually is going to be called drift velocity, and it is going to be denoted as VDN. This D is standing for drift, and this N is standing for electron. As you know, we represent our electrons as N. So that's actually going to be equal to minus nu N, which is actually going to be mobility, but we're going to talk about it later, times E. So this is actually a quite simple formula. You know why? Because here we have the drift velocity. That's easy. We know what it is. And here we have mobility, and I will explain what mobility is in a detailed way just a bit. Then here we have E, and that E is electric field. So here's the thing. For low doped silicon, the value of mobility is around 1350 centimeters square over volts seconds. And mobility actually can be considered as a parameter that shows how well an electron can move in a semiconductor. So you can basically think of that one as a unique future of an electron. So that's the mobility value. And as you can understand from the name, yes, mobility. How mobile are you, right? We are asking that question to the electron we have. And by the way, the negative sign in the equation represents the fact that electric field and also the drift velocity have opposite direction. And by the way, we can also see that in the figure, right? So that's the logic actually. We are making that drift velocity in the opposite direction with electric field. And by actually having this equation, so far we have explained the relationship between electric field and drift velocity. However, we also have another concept, which is drift current density. How are we going to calculate that? Actually, I'm going to give you the formula right away. So this J, which is drift current density, is going to be equal to minus E times N times VDN, and this is an important formula. So notice that in this E in here is charge, and this N in here is electron concentration, whereas this VDN, as I just explained, is the drift velocity we have. So actually this equation can be, rearranged a little bit. How so? So since we know that drift velocity, let me put that in here, drift velocity is equal to the electric field, right, times the mobility, and we also have the minus sign in order to make electric field and drift velocity to have the opposite direction. So if you replace this drift velocity value by the equation we have in here, so drift current density is going to be equal to minus E times N times minus nu N, and minus nu N is going to be the mobility, of course, times the electric field. This is going to be the equation we have, and in the end, actually, these two minuses will yield a positive sign. So the equation for the drift current density is going to become E times N times nu N times electric field. And actually, we know all the variables in here. This is basically the charge we have. And as I told you before, this N is electron concentration, nu N is the mobility for the electron, and E is the electric field. So drift current is in the opposite direction with drift velocity, meaning that it is in the same direction with electric field, and this is actually something important, something that you need to keep in your mind. So now what we're going to do is, so far we actually checked out an N-type material, meaning that that particular material by so far we have checked out an N-type material, meaning that it has more electron concentration than hole concentration. Now what we're going to do is we're going to check out a P-type material as it is written right in here and see what is going to be the drift current density. So now according to this P-type semiconductor, just like in the figure we have in here, when we apply an electric field, of course that exact electric field also creates a force, right? And that force is actually act upon our electrons and holes again. But this time actually we simply have a difference. And that difference is pretty basic actually. The holes here obtains a drift velocity. And let me put the formula for that. VdP this time, this D is standing for drift and this P is standing for holes. That's going to be equal to nu P times E. Here nu P is the mobility for holes, and also E is going to be the electric field. So for low doped silicon, the value of mobility is about 480 centimeters square over voltage seconds. And the reason actually the logic we have in here is that the positive sign indicates electric field and also velocity are in the same direction, which you can easily see on the figure. And this hole drift also produces a drift current density, and which is, by the way, denoted by Jp, just like Jn. So that Jp is going to be equal to, which is a quite similar formula that we have found earlier for an N-type material, is going to be equal to E times N times alright, that's a mistake. You know why? Because this time we are going to have a hole concentration. So E times P times mobility of the holes, which is nu P times electric field. And I think you know everything in this formula. So this Jp is going to be the drift current density, this E is the charge, this P is the hole concentration, and this nu P is the mobility of holes, and this E right in here is electric field. So drift current is in exactly the same direction with the flow of positive charge. What is that supposed to mean? It means that it is also in the same direction with applied electric field. And now actually we're coming to an end, but before that actually let us think that what happens when a semiconductor has both electrons and holes. Which formulas are we going to use? So here's the thing. Of course, a semiconductor has both electrons and holes, and the net current will be the combination of the equations we have found and declared so far. So let me say J net, which is going to be the net drift current density. That is actually going to be equal to E times N times mobility of electrons times and also electric field, plus E times P times mobility of holes times electric field again. And that is actually going to be represented as the sigma times electric field, that is going to be equal to 1 over P times electric field. So what are those anyways, right? We need to learn about them. So the thing in here is that whenever actually you take a parenthesis in here, let's take an E parenthesis, then what you're going to have is E times N times nu N plus E times N times nu P. Not N, but this is P. So that's actually going to be equal to sigma times E. So you can clearly see that this part is sigma, right? And this part is the electric field. And also, notice that we also have another relationship, which is that 1 over P is equal to sigma. Now, here we have the notations, but we also really want to know the names, right? So basically, this sigma is conductivity. And this P in here is resistivity. So these are really important because basically when you check out the equation, right now here we have an equation for sigma, that's fine. But in the end, when you check out, here we have J net, right? Which is actually called to be the drift current density. So basically it is a current. And on the right side, in the outermost, what we have is 1 over P times E. And I told you that P is resistivity. So E over P is going to be equal to current. So actually that's a really similar logic with Ohm's law, isn't it? So we are actually going to check that out. Let me scroll the page down a little. So what we're going to have in here is that we know P is equal to 1 over conductivity, and this P is called resistivity. I'm assuming that all of you guys have taken circuit analysis course before, and you have dealt with resistance of a resistor. And in there, we actually use the formula, which is R, resistance, is equal to P times L over A, where this P is resistivity, this L is the length, and this A is the area. So this is what we are talking about actually. And also, let me brighten your day. Let's say we are using the equation J is equal to 1 over P times E. Right in here, I want you to notice something. I is equal to, let me say V over R. So right in here, we have P, which is resistivity, and here we have resistance. And also here we have current, and here we have current density. That's also fine. And finally, the thing I want to show you is that here we have electric field, and here we have voltage. And notice that actually electric field occurs when you apply a voltage to the semiconductor. See? And it becomes clear that voltage and current are linearly related to each other, proportional to each other. That's the logic we have. And also, let me remind you the formula for conductivity, which might be really helpful. Conductivity is equal to nu N, which is the mobility of electron, times N, which is the concentration of electrons, times E, which is going to be the charge, plus nu P, which is going to be whole mobility times whole concentration times, again, electric charge. And remember that when we are actually able to change the concentration of electrons and holes, and right in here, we know that this N is standing for electron concentration. And this P is standing for hole concentration, right? And remember that we are able to change the concentration of electrons and holes in a semiconductor by doping. What is that supposed to mean? It means that conductivity can easily be manipulated in a semiconductor, and that's what makes them unique. And this is really important. As you can see right in front of our eyes, we have an equation for conductivity in a semiconductor, and it can easily be changed by changing the concentration of electrons and holes. And we already learned how to change them. We are adding impurities. That's called doping, and by doping we can change the conductivity. So we learned that for silicon, for instance, at T is equal to 0 Kelvin, it is insulator, right? But by adding impurities, we can make that a conductor, and we can also make that an insulator. So that's fascinating about semiconductors. That's why we are actually working on them. So this is actually the end of the video. If you have any questions, I will be more than glad to answer. In the next lecture, we're going to solve 2 examples about drift current density. That's actually really important, so you should also watch that lecture. So thank you for watching, and see you in the next one. Hello everybody, in this video we are going to solve an example about drift current density. So the first one says, calculate the drift current density for a given semiconductor. Consider a silicon at T is equal to 300 K, which is room temperature by the way. It is doped with arsenic atoms at a concentration of Nd that is equal to 8 times 10 to 15. So the important notation in here is that we have Nd, meaning that actually we have a donor impurity. And we are also asked to assume mobility values as given and assume the applied electric field is 100 volts per centimeter. So we're going to calculate the drift current density for that semiconductor. First of all, let me put out the formula. For the drift current density for any semiconductor, we're going to have J that is equal to the conductivity, which is sigma, times the electric field. We are actually going to accomplish this formula. We already know the value for electric field, so let me just say check. So we need to get sigma value, which is conductivity. So how are we going to get it? So we also know the conductivity formula. Our conductivity is equal to nu n, which is the mobility of electrons, times nu, which is the electron concentration, times charge, plus nu p, which is mobility of the holes, times p, which is the mobility hole concentration, times e, which is again charge. So what we're going to do at this point is that we already have the value for mobility of electron, mobility of hole, and we know the charge. But what about n and p, which are the concentration of electron and hole? So we don't know them. So first we need to calculate the concentrations of electrons and holes. First of all, we know that we have an impurity and we have a donor concentration, which is 8 times 10 to 15. And since we're working with silicon, we also know that Ni, which is the intrinsic carrier concentration, is 1.5 times 10 to 10. So that basically actually shows us that since Nd value, which is the donor concentration, is a lot greater than Ni, which is intrinsic carrier concentration, we can simply say the donor concentration is approximately equal to our electron concentration in the material. And we also have the formula N0 times P0 is equal to Ni squared, which is the balance between electron and hole concentration in a semiconductor material. And from that actually we can find out P0 is equal to Ni squared over N0, which is electron concentration, which we know that is approximately equal to Nd, and that is actually going to be, let me put that in here as Nd. And then in the numerical calculation, we're going to say P0 is going to be equal to Ni squared, which is 1.5 times 10 to 10, and square of that over Nd, and Nd value is 8 times 10 to 16, or 8 times 10 to 15. All right, let me put that in here. And when we do the proper calculations right in here, we're going to end up with having 2.8 times 10 to 4 for the whole concentration we have. Now we can easily move on to the second part of the question, in which we're going to find out the conductivity value. So I'm going to change my color, and I'm going to say conductivity is equal to nu n. As far as I remember, that was 13 and 50. Then we also have the concentration, electron concentration, which is 8 times 10 to 15. And then we have the charge, which is 1.6 times 10 to minus 19 for an electron. Then we're going to say plus. This time we're going to have the mobility of the hole, which is 480, times the concentration of hole, which is 2.8 times 10 to 4, times, actually, we are also going to have charge, 1.6 times 10 to minus 19. So if you do the proper calculation in here, this part is going to be 1.728, and this part is going to be equal to 2.1 times 10 to minus 12. So actually what we're going to do in here, we're going to ignore this value, because when you compare two values, two contributions, this one is a lot smaller than 1.728. So that's why actually we can simply ignore it, because it's going to be something like this, 1.72800000021. I mean, we don't care about that. So basically, our conductivity value, let me change my color again, is going to be 1.728. So this is the conductivity value we have, but the question is not done, because we are looking for the drift current density, which is going to be conductivity times electric field, and electric field is 100 volts per centimeter. So in the end, what we're going to have is 172.8 A over centimeter squared. This is the answer. And this A is, by the way, amperes. So this is the answer for example 1. And let's move on to example 2, which is right in here. This time we are asked to consider an N-type gallium arsenide at T is equal to 300 K, which is doped to a concentration of Nd 2 times 10 to 16. And also notice that this time again we have a donor concentration. Assume mobility values of electron is given and also holes is given. Determine the resistivity of the material. This time we're going to do something different because in the previous question actually we have found out the conductivity value for the material. This time we are asked to find out the resistivity, which is actually going to be the reciprocal of the conductivity. It is not that hard. And then actually determine the applied electric field that will induce a drift current density of 175 amperes per centimeter square. So this is actually a reverse engineering, but the question is pretty easy. So first of all, what we need to do is we are going to get the conductivity value. Then actually by having the conductivity value, we're going to take the reciprocal and we're going to find out the resistivity. So how are we going to do that? First, we know that conductivity is equal to nu N times E plus nu P times E. So nu N is already given, which is, right in here, 6800. That's fine. But what about the concentration of electrons? That is not given. So first we're going to find out the concentration of electrons and holes. How are we going to do that? Since actually we have a donor impurity, we're going to check out the intrinsic carrier concentration of gallium arsenide and also the donor concentration. So the donor concentration, which is Nd, is a lot greater than the intrinsic carrier concentration of gallium arsenide. One of them is having the value of 2 times 10 to 16, and the intrinsic carrier concentration is about 1.8 times 10 to 6. As you can see, the donor concentration is highly greater than the intrinsic carrier concentration. So what we're going to say is N0 times P0 is equal to Ni square. So finally, P0 is going to be equal to Ni square over N0, which can be replaced with an Nd, because since this is the case, so I'm just going to replace it with an Nd. So in the end, I'm going to find out my P0 value as 1.62 times 10 to minus 4, which is actually a really small value. Whereas our N0, which is the electron concentration value, is something about 2 times 10 to 16. So now what we're going to do is I'm going to keep on moving with the sigma conductivity formula. 6,800 times the the concentration of electron, which is 2 times 10 to 16, times the charge, which is going to be 1.6 times 10 to minus 19, plus the mobility of the holes, which is 300. That's fine. Times the concentration, which is going to be 1.62 times 10 to minus 4. And I'm sorry to put that in here, but I just need to move on. And the charge 1.6 times 10 to minus 19. And as you can see, this part is again ignorable, because when you calculate this part of the contribution, you're going to find out this is equal to 21.76. And right in here will be something like 7.76 times 10 to minus 21 or something. So as you can see, you can ignore this part totally. So the conductivity you're going to have is going to become 21.76. So this is good news. You know why? Because since we have the conductivity, we can easily get the resistivity. And when you think about the names of conductivity and resistivity, you can easily understand the logic behind them. You can see that one of them is the reciprocal of the other one, because one is conducting and the other one is resisting the current. So that's the logic. So resistivity, which is a weird P, is going to be equal to 1 over conductivity 1 over 21.76. In the end, what we're going to have is 0.046 ohms centimeter. So this is the answer for resistivity, and let me just say this is part A. And part B is a lot greater than part A, because in part A, actually, we have found out the necessary information we need in order to move on with part B. In part B, we're going to determine the applied electric field that will induce a drift current density of 175 amperes per centimeter square. So basically what we're going to have is this. We already know the drift current density J is equal to E, which is electric field, times conductivity, or E over P, which is resistivity. So in this story, actually, if we leave our electric field alone in such a case, then we're going to have our E that is equal to J, which is drift current density, times P, which is resistivity. And in that case, we know we are actually asked to find out the electric field for the drift current density of 175. So this is what I'm going to put in here. And also the resistivity value is 0.046. So in the end, the electric field we're going to have is 8.04 volts per centimeter. And this is the answer. And this is the end of the video. By the way, if you have any questions at all, please do not hesitate to ask us anytime you need our help. You can ask your questions by using Udemy's message box. Other than that, you can use our email address, or you can use our WhatsApp question line, in which actually we reply your questions as fast as possible. So it doesn't matter which platform or which messaging box you use, we will be replying your questions within 24 hours. So it is important for you to ask your questions, otherwise the learning process wouldn't be complete. So thank you for watching again, and see you in the next lecture, in which actually we're going to talk about diffusion. Hello everybody, in this video we are going to solve an example about diffusion current density. So the first one says, calculate the diffusion current density for a given semiconductor. Consider a silicon at T is equal to 300 K, that means we are at room temperature, and also assume that the electron concentration varies linearly. That's really important because we are actually about to get the derivative of the concentration. So it is important to have the information that it is actually varies linearly, because otherwise you wouldn't be able to calculate the derivative of the concentration. Anyways, it starts from n is equal to 10 to 12 and moves up to n is equal to 10 to 16 over the distance from x is equal to 0 to x is equal to 3 micrometer. Assume you have a diffusion coefficient which is 35 centimeters squared per second. So what to do right now is just we're gonna put out the formula. That's it. I mean, why am I even here, right? So Jn, because we're talking about electrons, is gonna be equal to E times dN times dN over dx. So basically, let me remind you, this is diffusion coefficient, and this is the gradient of the concentration. Let me just say gradient of electron concentration, and this E in here is charge. So the first thing we need to do is, we already have the value for charge, and we already have the value for diffusion coefficient, but we don't have the value for gradient of n. So let me calculate that. dN over dx is basically actually equal to the change in n, which is concentration, and the change in position. So in that case, the change in concentration occurs from 10 to 12 to 10 to 16, all right? And the distance change occurs from 0 to 3 micrometer, which is going to be 3 times 10 to minus 6. So now what I'm going to do is I'm going to put out the formula in here. So Jn is going to be equal to 1.6 times 10 to minus 19 times dN, which is 35, times this particular amount. My calculator will actually handle it. So 10 to 12 minus 10 to 16 over minus 3 times 10 to minus 6. And finally, you will have the answer as 18,664.8 amperes per centimeter squared. This is the logic we have. And let me remind you, by the way, the Jn value we have found is the diffusion current density due to the diffusion of electrons in the material. Now, we're going to solve another example, which is right in here. This time again, we need to consider a silicon at T is equal to 300 K. We're going to assume that the whole concentration is given as an equation this time. This question is a little bit different. This time we don't have a linear relationship. And there LP is going to be 10 to minus 3. Calculate the whole diffusion current density at A, x is equal to 0, and also when x is equal to 10 to minus 3, assume that you have a diffusion coefficient in an amount of 10. So how are we going to solve this problem? But again, exactly the same process, but this time we are having a whole diffusion. So Jp is going to be equal to E times dP times also dP over dx, but this time we are also going to have a minus sign since we're talking about holes. So in the end, actually, we have the E value, that's fine. We also have the diffusion coefficient, but we don't have the derivative of hole concentration. So let me actually get that. dP over dx is going to be equal to derivative of the expression we have right in here, which is 10 to 16 times e2 minus x over LP. So basically, we're going to take derivative with respect to x. So what we're going to have is going to be something like this. We're going to have minus 1 over LP, right, times 10 to 16 times e2 minus x over LP. And what we know is that LP is equal to 10 to minus 3. In a case, we're going to have minus 10 to 19 times e2 minus 10 to 3x. This is the final derivative we have for the, concentration of hole. So right now what I'm going to do is I'm actually going to get the whole equation, but in part A actually I'm asked to calculate the current density due to the diffusion of holes when x is equal to 0. In that case, what I'm going to have is JP is going to be equal to minus 1.6 times 10 to minus 19 times the coefficient value, which is right in here 10. All right, then I'm going to have this dP over dx, which is minus 10 to 19 times e to 0, because since x is equal to 0. And in the end, actually, what we're going to have is something around 16, not around, directly 16 amperes over centimeter squared. This is easy, right? And now we're going to do exactly the same thing when x is equal to 10 to minus 3. When x is equal to 10 to minus 3 this time, I'm going to have JP that is equal to minus 1.6 times 10 to minus 19 times the coefficient of diffusion, which is 10, times minus 10 to 19 times E2. This time notice that we have minus 10 to 3x. And if we put x is equal to 10 to minus 3, here we're going to have minus 1 only. So this is basically equal to 16 over E, where E is the number that you all know. So in the end, what we're going to have is 16 over E, which is going to be, let me actually check out my calculator. It is going to be something about 5.89 amperes per centimeter square. Right now, as in the previous lecture, I told you that I actually made a couple of warnings, but I also told you that I will repeat everything that I repeated in the last lecture in the example part. So I'm actually holding my word. So at this point, I want to give you a couple of extra information. The first one is, remember the mobility we have for the drift current, which is Mn or M. I mean, this is nu, by the way. This is called as nu, not M. So nu N and nu P, which are the mobilities for electrons and holes. Let me put that in here. This is mobility. And we also have diffusion coefficient, dN and dP. This is diffusion coefficient. So these are actually highly related to each other. They are not independent of each other. So the relevance between them is set up by Einstein's relation. So dN over nu n, dN is the diffusion coefficient for electrons and nu n is the mobility of electrons, must be equal to the diffusion coefficient of holes over mobility of holes, and that must be equal to K times T over E. And right in here, this K is called Boltzmann constant, and this T is temperature, and this E is charge. And now actually, if you pick your temperature at room temperature, which is K is equal to 300, T is equal to 300 kelvins, in the end, actually, this ratio will be something about 0.026. So this is really important. And also, if you are ever asked to get the total current density, in that case, you're just going to add the diffusion current density and also drift current density. It is that easy. And also, let's expand the idea behind current density a little bit. J is our current density, right? And it is actually equal to I over A, where I is the current we have and A is the area. So in the previous lecture, I gave you the example, but let me do that again. Let's say you have a fixed current density, which is 200 amperes per centimeter square, right? And let's say you are trying to create a current in an amount of 1 milliamperes. In that case, course, actually the area, which is going to be the size of the device, is really important, because since you know A is going to be equal to I over J, and what you have in here is 10 to minus 3 over 200. That's actually going to be 1 over 200. Let me calculate that. It is 5 times 10 to minus 3 times 10 to minus 3. In the end, your area must be 5 times 10 to minus 6. As you can, the device is really small when we think about such a current. So in the next lecture, we're going to talk about excess carriers, which is also really important. Thank you for watching, and by the way, if you have any questions, please do let me know instantly. I am always here to help you out. So thank you for watching, and see you in the next one. Hello everybody. In this video, we are going to solve an example about diffusion current density. So the first one says, calculate the diffusion current density for a given semiconductor. Consider a silicon at T is equal to 300 K. That means we are at room temperature. And also assume that the electron concentration varies linearly. That's really important, because we are actually about to get the derivative of the concentration. So it is important to have the information that it is actually varies linearly, because otherwise you wouldn't be able to calculate the derivative of the concentration. Anyways, it starts from n is equal to 10 to 12 and moves up to n is equal to 10 to 16 over the distance from x is equal to 0 to x is equal to 3 micrometer. Assume you have a diffusion coefficient, which is 35 centimeters square per second. So what to do right now is just we're gonna put out the formula. That's it. I mean, why am I even here, right? So Jn, because we're talking about electrons, is going to be equal to E times dN over dx. So basically, let me remind you, this is diffusion coefficient, and this is the gradient of the concentration. Let me just say gradient of electron concentration, and this E in here is charge. So the first thing we need to do is, we already have the value for charge, and we already have the value for diffusion coefficient, but we don't have the value for gradient of n. So let me calculate that. dN over dx is basically actually equal to the change in n, which is concentration, and the change in position. So in that case, the change in concentration occurs from 10 to 12 to 10 to 16, right? And the distance change occurs from 0 to 3 micrometer, which is going to be 3 times 10 to minus 6. So now what I'm going to do is I'm going to put out the formula in here. So Jn is going to be equal to 1.6 times 10 to minus 19 times dN, which is 35, times this particular amount. My calculator will actually handle it. So 10 to 12 minus 10 to 16 over minus 3 times 10 to minus 6. And finally, you will have the answer as 18,664.8 amperes per centimeter squared. This is the logic we have. And let me remind you, by the way, the Jn value we have found is the diffusion current density due to the diffusion of electrons in the material. Now, we're going to solve another example, which is right in here. This time again, we need to consider a silicon at T is equal to 300 K. We're going to assume that the whole concentration is given as an equation this time. This question is a little bit different. This time we don't have a linear relationship. And there LP is going to be 10 to minus 3. Calculate the whole diffusion current density at A, x is equal to 0, and also when x is equal to 10 to minus 3, assume that you have a diffusion coefficient in an amount of 10. So how are we going to solve this problem? But again, exactly the same process, but this time we are having a whole diffusion. So Jp is going to be equal to E times dP times also dP over dx, but this time we are also going to have a minus sign since we're talking about holes. So in the end, actually, we have the E value, that's fine. We also have the diffusion coefficient, but we don't have the derivative of hole concentration. So let me actually get that. dP over dx is going to be equal to derivative of the expression we have right in here, which is 10 to 16 times e to minus x over LP. So basically, we're going to take derivative with respect to x. So what we're going to have is going to be something like this. We're going to have minus 1 over LP, right, times 10 to 16 times e to minus x over LP. And what we know is that LP is equal to 10 to minus 3. In a case, we're going to have minus 10 to 19 times e to minus 10 to 3x. This is the final derivative we have for the, concentration of hole. So right now what I'm going to do is I'm actually going to get the whole equation, but in part A actually I'm asked to calculate the current density due to the diffusion of holes when x is equal to 0. In that case, what I'm going to have is JP is going to be equal to minus 1.6 times 10 to minus 19 times the coefficient value, which is right in here 10. All right, then I'm going to have this dp over dx, which is minus 10 to 19 times e to 0, because since x is equal to 0. And in the end, actually, what we're going to have is something around 16, not around, directly 16 amperes over centimeter squared. This is easy, right? And now we're going to do exactly the same thing when x is equal to 10 to minus 3. When x is equal to 10 to minus 3, this time, I'm going to have JP that is equal to minus 1.6 times 10 to minus 19 times the coefficient of diffusion, which is 10, times minus 10 to 19 times e2. This time notice that we have minus 10 to 3x. And if we put x is equal to 10 to minus 3, here we're going to have minus 1 only. So this is basically equal to 16 over e, where e is the number that you all know. So in the end, what we're going to have is 16 over e, which is going to be, let me actually check out my calculator. It is going to be something about 5.89 amperes per centimeter square. Right now, as in the previous lecture, I told you that I actually made a couple of warnings, but I also told you that I will repeat everything that I repeated in the last lecture in the example part. So I'm actually holding my word. So at this point, I want to give you a couple of extra information. The first one is, remember the mobility we have for the drift current, which is Mn or M. I mean, this is nu, by the way. This is called as nu, not M. So nu N and nu P, which are the mobilities for electrons and holes. Let me put that in here. This is mobility. And we also have diffusion coefficient, dN and dP. This is diffusion coefficient. So these are actually highly related to each other. They are not independent of each other. So the relevance between them is set up by Einstein's relation. So dN over nu n, dN is the diffusion coefficient for electrons and nu n is the mobility of electrons, must be equal to the diffusion coefficient of holes over mobility of holes, and that must be equal to K times T over E. And right in here, this K is called Boltzmann constant, and this T is temperature, and this E is charge. And now actually, if you pick your temperature at room temperature, which is K is equal to 300, T is equal to 300 kelvins, in the end, actually, this ratio will be something about 0.026. So this is really important. And also, if you are ever asked to get the total current density, in that case, you're just going to add the diffusion current density and also drift current density. It is that easy. And also, let's expand the idea behind current density a little bit. J is our current density, right? And it is actually equal to I over A, where I is the current we have and A is the area. So in the previous lecture, I gave you the example, but let me do that again. Let's say you have a fixed current density, which is 200 amperes per centimeter square, all right? And let's say you are trying to create a current in an amount of 1 milliamperes. In that case, actually, the area, which is going to be the size of the device, is really important, because since you know A is going to be equal to I over J, and what you have in here is 10 to minus 3 over 200. That's actually going to be 1 over 200. Let me calculate that. It is 5 times 5 times 10 to minus 3 times 10 to minus 3. In the end, your area must be 5 times 10 to minus 6. As you can, the device is really small when we think about such a current. So in the next lecture, we're going to talk about excess carriers, which is also really important. Thank you for watching, and by the way, if you have any questions, please do let me know instantly. I am always here to help you out. So thank you for watching, and see you in the next one. Hello everybody. In this video, we are going to talk about excess carriers, just a bit actually. This is going to be a really short lecture. I just want to give you the idea of excess carriers, and actually after this lecture we're going to solve some problems about the topics that we have covered so far. So up to this point, we have assumed that the semiconductor is in thermal equilibrium, which I have mentioned once before because I just did not want to confuse you. However, this is not the case all the time. For instance, in the discussion of drift and diffusion currents, we assumed that the equilibrium is not disturbed by anything, especially the diffusion, meaning that we always assume the stability of equilibrium. However, this is not the case. When a voltage is applied to a semiconductor, or when we have a current flowing through the semiconductor, the equilibrium is not achieved. Instead, actually, we are breaking the equilibrium. That's why actually we need to consider a couple of extra cases. And in this lecture, we're going to investigate the behavior of non-equilibrium electron and hole concentrations. So now, let's assume we have some high energy photons that interact with free electrons. So basically, I'm going to have some free electrons right in here. Then I will actually have some photons with high energies, all right? And those are going to interact with the free electrons I have. And actually, you have the information that the energy of these photons is h times nu from the semiconductors course. If you're interested in the semiconductor physics, then you can easily go and check Fundamentals of Semiconductors course that is created by Afterclap. Now, if this is the case, of course the electrons will gain some energy, right? Because photons have some energy, and when actually photons interact with the electrons, some of these energy will be transferred to the electrons we have. And this energy sometimes might be sufficient enough to break the bond for the valence electrons. So this is really important. You know why? Because when this is the case and when this is happening, one electron and one hole will be created. And thus, actually, we would have an electron-hole pair, all right? Because when we actually have the photon on our electron, thus the electron is actually gaining some extra energy, and due to that energy, it is breaking the bond. So, concentration and these additional electrons and holes are called excess electrons and also excess holes. This is pretty important. So other than that, actually, concentration of hole and electron would increase, obviously, right? Because we are having extra electron and extra hole, and that is actually really important when we take a look at the concentration of electron and hole in general. So the equation changes a little bit. So far, if you remember, when we are dealing with the electron and hole concentration, we use the representation as N0 and P0. I didn't tell you that, but N0 and P0 are actually standing for the concentrations at equilibrium, at thermal equilibrium. But right now, actually, we're going to make another definition for the electron and hole concentration. For instance, for electron, N is the concentration is going to be equal to N0 plus delta N, and I will explain you in a bit what this is all about. And P is equal to P0 plus, delta P. And here's the logic. First of all, let me turn off the notifications. All right, here what we have is N is the concentration we have, and N0 is the thermal equilibrium concentration. Thermal equilibrium concentration. And delta N we have in here is the excess electron concentration. And below equation is nearly the same with the previous one, actually. This time we're going to have hole concentration. This is thermal equilibrium concentration for holes. Exactly the same thing. Let me just say thermal equilibrium concentration. And this delta P we have in here, excess hole concentration. As you can see, this is a simple logic. We're just adding the additional concentration we gained due to the free electron and also hole. This is the logic we have, and as I said, this is going to be a really short lecture. This is everything about excess hole and electron concentration. There's one more thing that I want to mention. If the semiconductor is in a steady state condition, the creation of excess electrons and holes will not cause the carrier concentration to increase indefinitely, because logically, when you think about it, I mean, it is going to increase indefinitely, right? But no, that's not the case, because a free electron may recombine with a hole, which is called electron-hole recombination. I'm not going to dive into too much detail. Actually, I have dived into too much detail. I'm not promoting, but this subject is mainly about semiconductors, and we also have a separate course on semiconductors. If you want to find out more about these topics, please go and check that course. For now, since we are interested in electronics and since we are actually making an introduction, I will keep it as simple as possible. So in the next lecture, we're going to solve some couple of examples about what we have covered so far. So that's actually going to be a really nice one. So I hope you will be there. So thank you for watching. If you have any questions, you can always ask your questions or regarding anything. It doesn't matter. Thank you for watching and see you in the next one. Hello, everybody. In this video, we are going to solve some examples about the topics that we have covered so far. So the first question says, determine the intrinsic carrier concentration in silicon, germanium, and gallium arsenide at T is equal to 400K and T is equal to 250K. So what we're going to do is actually, I'm going to find out the intrinsic carrier concentration for silicon and germanium in both situations, but gallium arsenide will be your homework. So first of all, let me start with silicon. Let me just say silicon in here. So in part A, actually, we have T is equal to 400K, right? And in that case, actually, the intrinsic carrier concentration, let's remember the formula. It is B times T2 3 over 2 times E2 minus EG over 2KT. This is the formula we have for intrinsic carrier concentration. And it is not hard to remember what these variables stand for. This B is actually a coefficient that is unique to our silicon value. So this T is our temperature, this Eg is band gap energy, K is a constant, and T is again temperature. So what we're going to have in here is B for special, that is for silicon, that is going to be 5.23 times 10 to 15. Right, then actually we're going to have temperature, which is 400 in this case, 400 to 3 over 2 times E2 minus EG, which is going to be minus 1.1 and 2KT. So in the end, actually, if we evaluate this process properly, if you get the calculations done properly, you will end up with having 4.76 times 10 to 12 1 over centimeter cube. But what about the value of intrinsic carrier concentration when T is equal to 250 Kelvin? So in that case, again, we're going to have the intrinsic carrier concentration. And this time, again, we're going to have exactly the same B value, which is going to be 5.23 times 10 to 15. But this time, actually, the temperature decreases a little bit, 253 to 2 times E2. The band gap energy does not change. It is still going to be minus 1.1 over 2KT. And in here, finally, we're going to have the answer as 1.605 times 10 to 8. So one thing that I want you to notice is that as temperature decreases, as you can see, the intrinsic carrier concentration also decreases. And also, I want to inform you that this K in here is Boltzmann's constant, and the value for it is 86 times 10 to 6, I guess. Let me think, 5 or 6. It is probably 6, but all right, it is 6. As far as I remember, it is 6. So now let's move on with germanium. This time we're gonna put the title as germanium. And what we know is we're gonna get the intrinsic carrier concentration for T is equal to 400K. And this time, actually, again, we're going to have exactly the same formula. And I is going to be equal to B times T to 3 over 2 times E2 minus EG over 2KT. So right in here, this B value is different this time. It is not, again, 5.23 times 10 to 15 because each actually semiconductor has its own value for that. So this time, our B value is 2.10 times 10 to 14. And temperature value is 400 3 over 2 times E2. EG value this time, which is band gap energy, is going to be equal to 0.66, so minus 0.66 over 2 kT. And in the end, when you do the proper calculations, you're going to have, or let me put the result in here, when you do the proper calculations, you're going to have 9.06 times 10 to 14 1 over centimeter cube. But what happens if I just investigate exactly the same element, intrinsic carrier concentration, for T is equal to 250 K? So in that matter, actually, we're going to again say Ni is equal to B, which is 2.1 times 10 to 14 times 400 to 3 over 2, but this time we're going to have 250 to 3 over 2 times E2 minus 0.66 over 2 kT. And in the end, when you do the proper calculations, you're going to find out the answer is 1.42 times 10 to 12 1 over centimeter cube. So the result in here is that, again, exactly the same. As you decrease the temperature, also the intrinsic carrier concentration decreases. Now, the rest is homework. And what about the rest? The rest is calculating the intrinsic carrier concentration for gallium arsenide at T is equal to 400K and also at T is equal to 250K. You can send your solutions to me. It is important that you're solving these problems. And also please note that if you're not able to solve the question, you can always ask for a free one-to-one lecture. So now let's move on with the next question, in which it says, consider a silicon at T is equal to 300K. That's easy. Assume that the mobility of electrons is 1350 centimeters square volt second, and actually the mobility of holes is also given 480. Determine the conductivity and resistivity if Na is equal to 2 times 10 to 15 and Nd is equal to 2 times 10 to 17. Now, actually, we have two options. So we're going to take a silicon, right, and we're going to calculate the conductivity and resistivity in two different situations. The first one is actually we are having an acceptor impurity. In the second one, we are having a donor impurity. So first of all, let me start with part A. So in part A, what we're going to do is, let me say part A. Basically, we are having an acceptor impurity. Let me put that actually, because most of the students are not even aware of what we are doing. This time we are having an acceptor impurity. And the logic in here is that Na, which is the acceptor concentration, is a lot greater than the intrinsic concentration we have for silicon at T is equal to 300K. How do we know that? Actually, we have solved a couple of questions, and I told you that you should be given that value, or you can simply check out for the table. The intrinsic carrier concentration value for silicon at T is equal to 300K, which is basically the room temperature, is 1.5 times 10 to 10. Please keep that in mind. So, as you can see, 2.10 to 15 is a lot greater than 1.5 times 10 to 10. And that's the reason, actually, we're going to say P0 is approximately equal to Na. And so that actually we can easily calculate the value for N0, which is going to be Ni square over P0, which is basically Na. So in the end, when you do the proper calculations, you're going to find out the N0 value, which is the electron concentration at equilibrium, is going to be 1.125 times 10 to 5. Now, since we have both electron and hole concentration, we can easily calculate the conductivity for this material. Conductivity is going to be equal to N times E times mobility of electrons plus P times E times mobility of holes. And in that manner, actually, the concentration of electrons is 1.125 times 10 to 5. And charge is 1.6 times 10 to minus 19 times the mobility is 1350 plus the whole concentration is 2 times 10 to 15, yes, times, again, we have charge 1.6 times 10 to minus 19, and mobility is going to be 480. So this is the whole equation we have for conductivity. If you notice, this left whole part is going to be equal to 2.43 times 10 to minus 11, which is a really small number. And this right side is going to be 0.1536. So when you compare these two values, you can simply ignore this value because it does not affect the final answer we have. So basically conductivity is going to be equal to 0.1536. Basically that means the resistivity, which is the reciprocal of conductivity, is going to be equal to 6.51. This is the result for part A. And in part B, this time actually we are having a donor impurity, right? And how to understand that, basically we are given in the question as ND. So what I'm going to say is, let me first put donor impurity. This time again, we know that the intrinsic concentration for a silicon is 1.5 times 10 to 10 again. And notice that ND is a lot greater than Ni, which is intrinsic carrier concentration. We can easily see that because when you go up and, you know, compare the values, 2 times 10 to 17 is a lot greater than 1.5 times 10 to 10. And that's the reason actually we're going to say N0 is approximately equal to ND. And with that logic, we're going to say P0 is going to be equal to Ni squared over N0, which is ND in this case. And from that, actually, when you do the proper calculations, you're going to find out 1.125 times 10 to 3, of course 1 over centimeters cube, is going to be the concentration of holes. And then we can easily calculate the sigma conductivity value, which is going to be N times nu N times E plus P times nu P times E. And in the end, what we're going to have is the concentration of electrons is going to be 2 times 10 to 17, right? Then we have the mobility, which is going to be 1350 times the charge, which is 1.6 times 10 to minus 19, plus the concentration of holes, which is going to be 1.125 times 10 to minus, or not minus, positive 3, times 1.6 times 10 to minus 19, which is the charge, times the mobility, that is 480. So in the end, when you calculate this part, this whole part, it is actually going to be equal to 43.2, right? And this part is going to be equal to 8.64 times 10 to minus 14, which is too small, so you can definitely ignore that part. And finally, what you're going to have is your sigma value is going to be equal to 43.2, which is the conductivity, and we also have resistivity, right? And that is actually the reciprocal of conductivity, and that's going to be equal to 0.023. So these are the answers for part A and part B. In the next question, actually I was going to end this problem solving part right in here because we also have 3 more questions, so it would be fair to, you know, split up 2 videos equally. But I noticed that in question 3, it says, using the results of the second question, determine the drift current density if an electric field of 4 volts per centimeter is applied to the semiconductor. This is a really easy example, actually. You know why? Because let's remember, in option A, we were given a conductivity that is equal to 0.15 and 36, and also a resistivity that is equal to 6.51. And let's remember that our material was p-type. And in part B, actually, we again had this conductivity, which was 43.2, and also resistivity that is 0.023, and this time we are having a material that is n-type. So now what we're going to do is we're going to get the drift current density, which is going to be a really easy task. So JDP, which is actually, since we have a p-type material, that's why we have the notation in this way. This D is standing for drift, and this P is standing for holes, basically. That is going to be equal to electric field times the conductivity. So basically 4 times 0.1536, it is going to be equal to 0.614. And for this B option, we're going to have JDN, meaning that we are calculating the drift current for electrons. That's going to be equal to electric field times conductivity. Electric field is again 4 volts per centimeter, that is given in the question. And conductivity for this particular material is 43.2. So in the end, when we multiply these 2 values, we're going to end up with having 172.8. And of course, the unit is also important, amperes per centimeter square. And again, amperes per centimeter square. So this is the answer. And this is the end of the video. In the next video, actually, we're going to have 2 more examples, and we're also going to solve them. So these examples, I think, are really important in order to enhance your understanding on these kind of topics. I know the topics are a little bit hard to understand since they actually have this weird abstract side of them. I know they're a little bit confusing, but with actually solving more and more examples, I think you're going to get used to the area actually we are interested in. And also, let me remind you that this is an introduction to electronics part. So this is not the main subject that we are going to be interested in, but this is only the introduction, and it may include some information that you might not need later. So I'm sorry for that, but this is actually the basic information that everybody has to have before getting into electronics. So this is something that I have to do. So thank you for watching, and by the way, if you have any questions regarding the examples that we have solved in this particular video, or anything regarding the course at all, or it doesn't have to relate anything about us, all right, just ask your questions. It doesn't have to be about